When it comes to interesting questions concerning solutions, one that springs to mind almost immediately is, can I make this solution? I can certainly write down the AQ phase designator next to any conceivable solute and imagine that solute dissolved in water, hypothetically. But will that happen? Do the laws of thermodynamics permit that to happen, for example? Another way to phrase this question is the formation of a solution from the separated solute and solvent phases spontaneous or not? And by spontaneous, we mean a process that occurs without outside intervention. Can I simply mix the solute and solvent and expect them to form a solution phase on their own? A non-spontaneous process, in contrast, must be driven by an input of energy of some kind. And that's inconvenient, and precipitation or separation of the solute and solvent will occur as soon as that driving force is removed. So really we're trying to look here for conditions under which solution formation will be spontaneous. And dissolution tends to be spontaneous when two things happen. First of all, the internal energy or enthalpy of the system decreases. And here we're thinking about the system as the solute and solvent phases. When I mix them, if the enthalpy of solution formation is less than 0, if solution formation is exothermic, this will tend to make that process spontaneous. The second point here is that dissolution will tend to be spontaneous when matter and energy are dispersed. And I actually had originally listed that this is true for all dissolution processes, but it's not. While it may seem like dissolving a solute in a solvent allows those solute particles to spread out and disperse themselves, for gaseous solutes, this may actually represent a concentration of the particles in a smaller space. If we're trying to cram a gas that wants to take up the full volume of a container into a relatively small liquid phase. The punchline of this second bullet point, though, is that dissolution tends to be spontaneous when the entropy change associated with forming the solution from the separated solute and solvent phases is positive, when there's an increase in the solution entropy relative to the separated phases. And again, this tends to be the case, particularly if we're talking solids and liquids, but for different phases, it may not be the case. The detailed thermodynamic analysis of solutions can get pretty complicated if we have to deal with the details of intermolecular forces. To massively simplify the way we think about solutions, we can think about them in ideal terms. An ideal solution is one in which the intermolecular forces in the separate solvent and solute phases are equal in strength to the intermolecular forces in the resulting solution. Because those intermolecular forces are rooted in enthalpy and changes in IMF strength translate into changes in enthalpy, the thermodynamic implication here is that the enthalpy change of solution is equal to 0. With those intermolecular forces equivalent, in some sense we can ignore the intermolecular forces completely. And what this means is we can make a profound simplification in thinking about the solutes and solvent as ideal gases. And this works best if the solute and solvent are gases themselves, or they're liquids with similar types of intermolecular forces, things like methanol and ethanol, which can both hydrogen bond and have fairly similar molar masses, very similar molecular size and shape, this kind of thing. So check out this very simple experiment shown here in this figure. We start with helium in one vessel and argon in another, a solute and a solvent, if you like, or vice versa. Then we open the stopcock or the valve between and allow the gases to diffuse into one another so that we get equal composition of both gases on both sides after some time when the solution reaches equilibrium. At this point, I've got a solution in the left-hand container and a solution in the right-hand container. And assuming both gases are ideal, these are ideal solutions. And they really provide an archetype for thinking about any ideal solution. An ideal solution can be treated at a very deep level, like a simple mixture of ideal gases with not just equivalent intermolecular forces between the particles, but no intermolecular forces between the particles. There's a subtle difference there between those two ideas, but it's not one that we'll need to wade into in an introductory course. The right mental model here is to think of the solute and solvent as ideal gases at this point. Let's talk about the thermodynamics of solution formation. So imagine our reactants were the two boxes you see up here, a solute phase and a solvent phase, completely separate, completely intact. So there are intermolecular forces going on within the solute and within the solvent. And if we peek ahead to the final solution, we see that the solute and solvent particles have to some extent been separated from one another in the final solution. So we need to disrupt the intermolecular forces within these pure phases, pure substances, in order to get to the solution point. However, we're also making new interactions between the solute and solvent particles, and this is key to appreciating the thermodynamic analysis that's about to happen here. So one way to imagine a solution forming is to first explode, quote unquote, the solute and solvent particles, breaking the intermolecular forces within those pure substances so that we can fill in the other particles into the empty space. That's going to require destruction of intermolecular forces. Once we've done that for the solute in step 1 and the solvent in step 2, we then allow the two to mix, and this creates new intermolecular forces in step 3, and we've arrived at the solution. Now let's think about this in terms of enthalpy change. In step 1, we're destroying intermolecular forces in the solute. We are breaking solute-solute interactions. This implies that this step is endothermic. So delta H for this step 1 is going to be greater than 0, positive. Likewise with step 2 for the solvent. We are destroying solvent-solvent intermolecular forces in this pure phase, and so this step also will be endothermic. However, when we bring these two expanded phases together, well, now we're making intermolecular forces between the solute and solvent, and so for this third step, delta H will be negative, the step will be endothermic. Now let's ask about the overall enthalpy change of solution formation, or just enthalpy of solution for short. The enthalpy of solution here we can reason through using Hess's law. The solution process is step 1 plus step 2 plus step 3. So the overall enthalpy change will be delta H1 plus delta H2 plus delta H3, where I'm color coding the delta H's based on whether we expect them to be endothermic, positive, or exothermic, negative. Now we can see a basic criterion for exothermic solution formation is that negative delta H3, or the magnitude, if you like, the absolute value of delta H3 must be greater than the absolute value of the sum of delta H1 and delta H2, both of which will be positive anyway, so we don't need an absolute value or negative sign on the right-hand side. It must be more exothermic to create these solute-solvent interactions than it is endothermic to destroy the solvent-solvent and solute-solute interactions in steps 1 and 2. If that's the case, solution formation is exothermic. And many exothermic solution formation processes are spontaneous, but not all. And there are some endothermic solution formation processes that are spontaneous. Certain cations and anions are famous for this kind of thing. They still dissolve even though dissolution is endothermic. So while this can be a useful guideline for predicting spontaneity, it's not a hard and fast rule. The real beauty of this analysis, in my eyes, lies in the way it gets you thinking about how intermolecular forces change as a solution forms. We are destroying solute-solute interactions and solvent-solvent interactions and creating solute-solvent intermolecular forces. In solutions associated with very strong solute-solvent interactions, we generally expect the solution to form relatively easily and in an exothermic manner, releasing heat.